did a bit of talking last week about around how any regularly repeating waveform can be expressed as a series of sine waves with different frequencies, harmonics. So with the fundamental, if we've got a fundamental of 100 Hertz, second harmonic is 200 Hertz, third harmonic 300 Hertz, and so on. And that you can make up or express any repeating waveform as a series of sine waves, cosine waves added together. Okay, so the basis of that mathematically is Fourier series. I'm not going to spend a whole lot of time on this, but I want to show you where it comes from, that we can represent a square wave through a repeating series of third harmonics. Okay, so the basis of Fourier series is that all functions of practical significance, which are defined between the values of x is greater than from minus pi to plus pi, can be expressed in the term of a convergent trigonometric series of the form. And then we've got here A0 is the DC component we talked a little bit about last week. So that component will shift the whole waveform up and down the y-axis on any graph. Okay, and then we got a series of cosines terms, like so, with that being the fundamental cosine term, that's the second harmonic, that's the third harmonic, and we can carry on adding lots of them if we want to. And then with the B constants, they're the sine terms, first harmonic sine term, second harmonic sine term, third harmonic sine term, and so on. So all these constants, A0, A1, A2, B1, B2, etc., are real constants. They're the fundamentals. Multiply x by 2, we've got the second harmonic, 3 the third harmonic, and we can go for as long as we like to the nth harmonic. Okay, so what we're going to have a look at, what we're going to be having a look at this week is how we determine these constants, A0, A1, A2, B1, B2, and so on. Okay? So, in terms of integration, so that whole series can be written as an infinite. These series can be written as an infinite series. So we got the A0, the DC component, is always up front, and then we add the sum of these functions between the value of n equals 1 to n is equal to infinity. That's an infinite series. Okay. By the way, I'll just go back to the first page, something I didn't explain. What it means by convergent is that these terms, A's and the B's, are getting smaller as you go through the series. That means it's convergent towards, so the amplitudes will be convergent towards 0. Okay? That's what that means. So, we can find the constant term, the A0 term, from 1 over 2 pi times the integral between minus pi and plus pi of whatever our function is. Each term an we can find from 1 over pi the integral of between pi and minus pi of the function times the cosine of nx, and then we find the b terms from 1 over pi integral between minus pi and pi of the function times the sine of nx dx. So this involves some integration back from what we did in maths last year. I don't expect all of you have got your tables of standard integrals and derivatives handy from maths, but I'll put the two that we particularly need on the board. I'll put the ones we need on the board anyway. Okay. IO, IN and BN are called the Fourier coefficients of the series. in electrical terms, that's where your amplitude comes from for each of the components. Alright, we'll look at an example square wave with an amplitude of 1, I think I give it 2 to start with, but then we'll look at what happens when you put a constant in for that to see where the amplitude fits in for our electrical sine wave. Alright? Everyone reasonably happy so far, apart from the complex mathematical nature of what we got on the board there. We'll go through the example and I'll do the first little bits together, and then you can have a go at the later harmonics later on. Okay? So, what we're going to do is look at an example and obtain the first 3 terms of the Fourier series for the square wave. We've got the square wave that starts off at minus pi, goes negative to 1, and then up to plus 1, and at pi goes back to 0. So we've got a repeating square wave function. We can define that. How do we define? This is not a continuous waveform, because at that point it jumps all the way from minus 1 to 1. So you have to express it in as 2 separate values. We have to say when x is equal to minus 1 for values between minus pi and 0. So the function is equal to minus 1, and the function is equal to 0, so is equal to 1 between 0 and pi. Yep, and we have to deal with those 2 parts separately because it's discontinuous. So let's have a look at how we go about doing that. First of all, determining the DC component A0. That's the formula that we've got to use. So we need to do 1 over pi times the integral between minus pi and pi of the function f of x dx. That's what we've got to do. So, because this thing is discontinuous, we've got 2 values for the function. We need to separate that. So we're going to do A0 is equal to 1 over 2 pi, some big brackets, and then we have to do the integral between 0 and minus pi of minus 1. That comes from here. Plus the integral between 0 and plus pi, where the function is 1. So we integrate those 2 separately. The integral entry from the table that we want here is the integral of I dx is equal to Ix plus C. Remember that from last year or not? So what we're saying is if we integrate a constant, the variable comes back plus the constant of integration. Yep. So what's going to happen here? What do we think? If minus 1 is a, what's it going to be when we've integrated? Minus 1x. What about here? 1x. Or just x. Yep. So, this is what we've got from that. 1 over 2 pi, outside some brackets. And then this integral is between minus pi and 0. That's a definite integral there, because we've got limits of minus x, plus the definite integral between 0 and pi of x on its own. Anyone remember how we solve definite integrals? Did I tell you at the end of the last year you could forget all the maths you'd done in computational analytical methods? For just this bit, we have to say that bit there is equal to, and then we have to put the higher limit in, so that's minus 0, I'll put that in some brackets, minus pi. So we've put that value in for x, and then that value in for x. And you do the same with this one. So we end up with is that 1 over 2 pi times 0 minus pi. So that 0 comes from that limit, the top limit in the left-hand one. The minus pi is the lower limit. And then here, pi is the upper limit, 0 is the lower limit. Where's that here? Yeah, but you've got minus pi plus pi. What does that make? What's no. Put it in your calculator if you're unsure.
Yeah, because I know it's minus x, you can't have minus 0.
No. Well, that's effectively minus 0. But if you put it in your calculator, that come out as 0, I can assure you. I mean, these two terms don't even need to be there, really, do they? You've got minus pi and plus pi is nothing. All right, everyone agree now? Oh, hang on. They do come, I beg your pardon, those come out of 2 pi, but then you've got 1 over 2 pi times 2 pi is nothing. Yeah? Well spotted, that man. Sorry. Right, anyway, next page. We're going to have a look now at determining the AN terms, so that the terms in front of the cosines, if there are any. I should point out there's not always an A0 term. Some functions there aren't any cosine terms. Some functions there aren't any sine terms. Some functions there's both. Okay? So, we're going to look at determining the AN terms. Often becomes apparent there's a pattern to the coefficient values. For example, only odd or only even have a value. So sometimes, as well as there not being any cosine terms, there might be only odd terms or only even terms in the function as well. All right. So you can only find that out through doing the first few, and then you can see a pattern to them. So what we're going to do first is try when n is 1, i.e. we're talking about the fundamental in any complex waveform here. We need to do 1 over pi times the integral between pi and minus pi of the function times the cosine of x. So again, we need to do it separately because it's discontinuous. So this bit is for values of x between 0 and minus pi, and this bit is for values between 0 and plus pi. And the integral in the table we're looking at here is the integral of, we already know how to do fx because we got it there. One we're looking at here now is cosine, and so that's the integral of cos ix is equal to 1 over a sine ax. So that's the one we're using now. So what's the constant in front of x inside these cosines? 1. Yeah? So when we, that's whatever a is in this particular one, a is 1 in this example. Yeah? So when we integrate that, that's what we get. 1's coming down, so we stay with minus 1 in front here of sine x. That's between minus pi and 0. Again, the 1 comes down. 1 times 1 is 1. Sine of x. That's between 0 and pi. Reasonably happy so far? Yeah? So what we've got then is this bit here is this definite integral of this bit here is that definite integral. So we've taken the top limit out and put it in there, minus the sine of 0, minus sine of minus pi. Where? No, because that's the lower value, isn't it? Lower value, upper value. Possibly. What here? Yeah. Minus in there. I'll spot a jack. Getting used to my typos by now, guys, aren't you? Alright. Sine of x, sine of pi, top one. Sine of 0, bottom one. Let's have a look under there. What is minus the sine of 0? Nothing. Didn't really make a lot of difference, Jack, at the end of the day. Take away minus the sine of minus pi. It's the sine of minus pi. Zero. plus the sine of pi nothing, minus the sine of 0, nothing. In other words, all of that is 1 over pi times nothing. There is no A1 term. Okay? So I've made a statement there, A1 equals nothing. So there is no first cosine term. There's a lot of writing for nothing, but you kind of got to prove it. You can't just, if I just tell you there are none, well, why am I telling you that? Whereas that proves it. Yeah. So, there's no first cosine term. Have a go. Is there a second cosine term? What have I got next? Hang on, what have I got next? No B terms. So what we're now talking about, n is the number of a harmonic, effectively, we're dealing with. So if just going back to a bit further, and one more. We're adding together a series of, an n is the number in front of the frequency, so that's the number of the harmonic. When that's 1, that's the fundamental. When that's 2, it's the second harmonic. When that's 3, there's the third harmonic. And we must check the second one. We've got no first cosine term, but we must check the second one because there could be even terms, but not odd ones. Do you see where I'm coming from? So we've checked an odd, we've checked the 1, we need to check when n is 2 as well. So let's take a look. Should have that as your function to integrate. 1 over x, and then this half is for between minus pi and 0. This half is for the bit between 0 and pi. You integrate that. I've done it again, haven't I? Oh. Okay. I love adding colour. So, I was in a hurry when I done this one. That bit is due to that bit is due to that bit. Ultimately, I didn't make a mistake because nothing over 2 is nothing. And 1 over pi times nothing is nothing. There are no cosine terms in the square wave function Fourier series. Okay, but we've proved it. Yep. If you know your sines and cosines, and you know that the sine of 0 is nothing and the sine of pi is nothing, and the sine of 2 pi must be nothing as well. So you can see that, and that doesn't make any difference that I've accidentally not put the divide by 2 in. Right. So, having determined that A1 and A2 are 0, we can make the deduction that there are no cosine terms in this series. So next thing to do is have a look for the Bn terms, the sine terms. So that's the integral we want to use here. I've got n in it this time, Catherine, up there, but not here. I definitely didn't have a good day when I put this together, did I? Oh, well, never mind, it's done now. We're all human, we're all fallible. Alright, so the integral we're looking to use this time is that the integral of sine AX is equal to minus the cosine minus 1 over a, sorry. 1 over a cosine AX. So, there it is. This half is the values of x, values between minus pi and 0. This half between 0 and pi. Let's see if I've done it right this time. I bet I've done it wrong again. No, can't get that one wrong because we're dividing by 1. Yeah. So this half becomes the indefinite integral between minus pi and 0 of 1 cos x. And this side is the definite integral between minus 1 cos x between 0 and pi. Have I got my plus and minus signs right this time? Yeah, because that minus sign coming out of the cosine is cancelled by this negative 1 here, isn't it? So that's definitely plus 1. But that one's minus 1 times plus 1 minus 1 cos. Alright? Which separates out to that. So we put 0 in the first term on that side. So these two, there and there, coincide with each other. And that one and that bit coincide with each other. Yeah? Everyone agree with me? Have I any mistakes there you can see? You're good at spotting them today. This is a good thing. Cosine of 0 is 1. Cosine of minus pi is minus 1. Cosine of minus the cosine of pi is 1. Minus the cosine of 0 is minus 1. So, first B term, the fundamental coefficient for the fundamental is 4 over pi. One minus minus 1 is 2, plus another 1 is 3, minus minus 1 is 4. All okay with that? Yeah? Let's have a look at it a bit at a time. So, we got a fundamental How about when n is 2? We put the function in 2 halves. Oh, I got this one right, look. Divided by 2. Give myself a house point. So these two bits coincide with each other. And these two bits coincide with each other. Separating all of that out. So that bit goes with the red. That bit goes with the green. And then evaluating each of those terms in the calculator. Cosine of 0 is 1, so that's 1 over 2. Cosine of minus 2 pi is 1. That's 1 over 2. Minus the cosine of 2 pi is minus 1. Minus the cosine of 0 is minus 1. So we've got 1 half. Minus a half is nothing. Plus minus 1 over a half. Minus a half. Minus 1 over half. Plus that half, so the whole thing evaluates to 0. 1 over pi times 0 is nothing. So there's no second harmonic term. Yep. What we can say, if we know our sines and cosines well enough, we can make the statement that when this is changed to cos 4 pi or cos 6 pi, they're still going to evaluate so that they cancel each other out and end up as 0. And therefore, the only difference is going to be when it's 4 pi, these are going to be quarters, and when it's 6 pi, they're going to be sixths, but they'll still cancel out, and therefore there are no even harmonics at all. They'll all evaluate to nothing. So all the even b terms will be 0. Yep. So, how about when n is 3? I'll leave you to do that one. Really simply a task of, if we got the previous one, that when n was 1 correct, when n was 2, we can replace the 2 with the 3. So we end up with these two terms coming from each other, these two terms coming from each other, and the only difference is that 2 has been replaced by 3. Again, we write out the definite integrals in full. Evaluate the cosines on top. They all evaluate either to 1 or minus 1. So we've got a third, minus minus a third is 2/3, plus a third is 3/3, minus minus a third is another third, so that's 4/3. So the result is 4/3 pi. So the B3 coefficient is 4/3 pi. And then once you can realise there's a pattern coming to this. So if we consider when n is 5, again that's a matter of replacing the 3's with 5's, like so. So we end up with fifths in there, but the top line is the cosines still evaluate to the same value on the top, and therefore we got this repeating pattern. The fifth is 4/5 pi. The seventh would be 4/7 pi, seventh harmonic. Ninth, 4/9 pi, and so on. Okay? Yeah. So from that, it should be evident that for odd values of n, Bn, the coefficient, B coefficient of number n, is 4/n times pi. In this case. Okay, now pi would be, and possibly the number 4 be different if we are talking about a different period, the frequency. I'm not going to go into functions that aren't between minus pi and pi, where what we'll be talking about as functions that have got a different frequency to this. Alright, I'm not going to be doing that. Okay? So, what I just wanted to do was, lastly, look at where the amplitude of the square wave comes in to that resultant function. And I suppose what you really ought to have done was put, I have got it on the page, that is effectively, we can write the first 3 terms as that. So this is the n equals 1 term, fundamental. This is the n equals 3, the third harmonic. And this is the n equals 5, fifth harmonic. And now we know what the pattern is, we carry that on indefinitely and make it an indefinite series if we wanted to. Right? So, what happens when the amplitude is not 1? So I've done the example with the amplitude equal to 1, just to keep things reasonably simple with the maths. But how about, what would that look like for an amplitude of, and I've used an arbitrary letter k. So let's assume the amplitude of our function is between minus k and k, i.e. the amplitude itself is equal to k, because when we talk about the amplitude, it's from 0 to the 1 peak, not from peak to peak. When n is equal to 1, and we know for a square wave now that we're only going to have odd harmonics, we're not going to have any cosine terms. Yep, so we only need to look at the functions for the b terms in this. Okay. We also have kept it central around the x-axis, so we know there's no a0 term either. There's no DC component here. So we put in B1, okay, there, 1 over pi, that's the function we've got to use. And then we enter, and instead of putting -1 and 1, we put k, I'll put k in. So there's the red side, there's the green side, keep it consistent. We've got to integrate those two terms. Which I've done there. Everyone agree with the plus and minus signs? Yeah. Write that out in full. All right. This evaluates to 1, and therefore overall is k. This evaluates to -1, so that's minus k. Third term evaluates to cos pi is 1. So that should be that does evaluate to plus k. So we got k, now plus another k is 2k, plus a third k, plus a fourth k. So we've got 4k over pi for B1. So that's where our amplitude goes on the top line there. Okay? And then lastly, just see what happens. We know we've got no second harmonic, but we know we're going to have a third harmonic. Let's go all in one go. So we've got 3 come underneath here, but we end up with the same thing on top, k and minus k, k and minus k, the thirds underneath. So the amplitude is still just k on the top, but it's been divided by a factor of n, the harmonic number. So the amplitude is going to be reduced by a third for the third harmonic. Yep. So what's B5 going to be? Should be apparent from this that for a square wave with amplitude k, the coefficients for odd values of n are 4k over n pi. Yep. Adrian? Not too bad actually. Yeah.
Grade center, Mike. There's nothing there. There are no assignments. Nothing.
No.
So do we put that? Do I have to create? They create it as an assignment. In other words, progress presentation.
Yes.
But nothing. I won't put anything up there.
No.
Other than to
No.
set it.
Yeah. Yeah. Then you'll have a grade to put it against.
And then I can open up. And,
Yeah.
all right.
Yeah.
Okay. So I'll set it as an assignment.
Yeah. Because there will be for the final report, won't there? Yeah. But was there not anywhere where he handed in his, or did he just send his proposal to us
Well,
then?
that's an interesting one, isn't it? So should I put that up as well? Proposal.
Well, it ought to be there, didn't it?
And we gave it.
Yeah. Would you mind doing that?
What we gave it, like,
I can't remember off the top of my head.
we actually.
I'm sure we can find it somewhere, but I can't remember off the top of my head.
Okay, so proposal, progress.
Sorry about that, Adrian.
That's 5%.
I'm not in a,
10%.
yeah, I'm not doing very well at the moment. I keep making mistakes. But there we go.
Making mistakes.
Yeah, well, just not getting things done and forgetting things, and an odd one or two mistakes in my board slides today, where I kind of copied and pasted stuff and then not changed some things.
Oh, right.
It happens.
It does.
They're spotting them, so they're at least awake, aren't they?
What?
Oh, I left that running, never mind. So, on the last page here, what I've done is tested that out with a square root of amplitude 25. So in summary, what we can say is that a square wave can be expressed as a series of odd harmonics where the amplitude of each harmonic term reduces by a factor of the harmonic number. We've proved that. I kind of told you that last week. Now we've proved it through Fourier series. i.e., the amplitude of the third harmonic is 1/3 of the amplitude of the fundamental. The amplitude of the fifth is 1/5 of the amplitude of the fundamental, and so on. So a square wave of amplitude 25 volts and angular frequency n can be represented by 25 sine nx plus 25 over 3 sine 3nx plus 25 over 5 sine 5nx, and so on. Okay? The more harmonics that are added, the closer we get to the exact square wave, which we could represent by an infinite series. Alright? Now, you might be thinking, where's the point of all this? But what we're really interested in is this issue over the possibility of unwanted resonance in a circuit with one of these harmonic frequencies from the input of that square wave. Because we're saying that square wave is made up of these harmonic frequencies. And we got an issue, we could have an issue if we end up with, or these are unwanted harmonics, and then we end up with a series resonance situation in a circuit. And that we're going to look more seriously at that in the next session. Okay? So square wave with mains kind of voltages, this is where it could become a big issue, and you end up with thousands of volts across components and high currents flowing. When you speed control induction motors, you use something called an inverter. And what an inverter drive does is, in its very basic sense, and I always say, it takes the 50 Hertz AC main sine wave, and it rectifies it to DC. So let's say 400 or 600 volts DC, and then uses a microprocessor to turn that back into a sine wave, but at variable frequency. And the way it varies the frequency on some of the drives is to use a very fast switching square wave to recreate that sine wave. And so therefore, if you don't filter it properly, you've got the potential of this harmonics issue. Okay. The other thing is, and I've got something in the bird book I can show you, is if we have, when we get a waveform like this, yeah, bridge rectifier, full wave rectification. The example I've got is only 5 volts, but it could be much higher than that. So first thing you do is, as Lewis said, bridge rectify the AC waveform. Effectively, you take the half cycle that's underneath here and turn it up the other way and put it on top of the line. That waveform is DC, because if you apply it to a circuit, current will only ever travel in one direction. It's changing as time goes on, but it's not crossing this 0 volt line for its DC. So we've rectified our AC to DC. If this is a function 5 sine theta over 2, and bear in mind we kind of switched a little bit from time into angles, but that doesn't really matter for this example. Okay. The third series pi 20 of a pi half minus theta over 3 minus cos 2 theta over 3 times 5 minus cos 3 theta over 5 times 7. And as you can see, once again, there's a pattern. Yes, that you've got, what's this half here? What's that representing? The DC component, yeah. All of this is above the line. Therefore, there must be a DC component. That's averaging positive, isn't it? Yeah. So that represents the DC component. This one. First harmonic, fundamental. Second harmonic. Third harmonic. And so on. So in this series we've got no sine terms, we've got cosine terms, and we've got both even and odd cosine terms. Yeah. Okay. I don't propose to go through all the maths it takes to get to that, because that's 2 full pages in the Bird Higher Maths book, and there's no point. Okay. The idea of showing you it is to make you aware that even that kind of function can have harmonics in there that could be an issue in some circumstances. If you use thyristors to drive circuits, they kind of do half the sine wave and then drop off, or they fire halfway through. You get some odd wave shapes. They'll be full of harmonics. You need to be careful with, particularly if the voltages are high and there's a chance of series resonance we're going to look at next time. All right. In terms of the exam, I'd imagine the most I'll do is ask you to find one coefficient, and you'll be given, the formulas will be in the formula sheet, and the standard integrals would be in the formula sheet if they're needed. Not going to be asking you to do all that lot, okay, because that would just be too much in a 1-hour exam. We won't have time for anything else. But I think it's important that rather than me just telling you, a square wave is odd harmonics only, and that reduced by the harmonic number, just prove it using Fourier series. All right. We got through a little bit more than I expected today, so we got a little bit of an early finish. All right.